Draft science video from the out of doors. Really just too nice a day not to not to do this out here. So anyway, Hafla Day is defending Piro's irrational. No, it's not irrational. It's just retarded and sloppy, just completely wrong physics. Just wrong. And he's defending it. And I thought they were like sloppy and reckless, in terms of they've really not really thought about this. They haven't done what I've done, which is spend all my free time thinking about this. So yeah, they have these little notions in their head and they haven't really thought about it. And that's what I kind of thought it was. But it's got to go deeper than that, because they're being so belligerent in getting completely the wrong answer, and so arrogant, and it's just amazing. And this is disputing their own Einstein. I'm in this ironic position of defending classical Einsteinian type physics against these people who are supposed to be the defenders of this mush. Again, they don't read their own Bible. They don't understand their own Bible. So I thought of another way to analogize it, like the sun and heat. Yeah, heat units maybe. But let's go through a couple of things. Well, it's this density argument. So look, ultimately all you can think about this is that this is like the proton and electron, right? And we know that attraction is very strong. Well, that's all gravity's working on. So all you're really thinking about, if you're thinking properly, is how much attraction is there at the distance I am between electrons and protons, because that's all that's really running the show. That's the source of the force, so to speak, the bent space. That's the real source of the bent space. Or you can think about magnets and just how quickly, their ability to influence each other diminishes. Just go a little bit away with a compass needle, with a magnet, and all of a sudden the magnet can't do anything. Can't make the compass needle move at all, because it's the inverse square law is taking effect. So my first premise argument here is, even if you had a galaxy, all right, first let's do the basic argument again, just one more time. We see in the image a galaxy pie in the face. All right, we don't see it on edge. We see it pie in the face. That means the gravity the light has to go through is the thinnest part of the galaxy. So if you understood the galaxy to be made of objects that are making the gravity, you could sort of understand that if you're going this way across that galaxy, you're really, really far away from that sun there. And really far away from that one, and that one, and that one, and that one. Most of them you're really far away from. And their gravity is going to be very, very uninfluential on you. But if you went this way, across the length of the galaxy, not only would you be in the gravity longer, not only would your lens have... See, another thing they're ignoring is that the smaller you make the object... excuse my coughing. Maybe outdoors wasn't a great idea. The smaller you make the object, the less the light has to bend. You see, less bending with a small object. And the bigger you make it, the bigger the lens is, the galactic lens, the stronger the gravity has to be, because it has to bend from a wider position. So that's another thing against them. So not only are they going through the thinnest part of the galaxy, they have to bend a much wider angle because of this longer distance. You get it? If they went through the thin part of the galaxy, if the galaxy on edge, the distance is only this far, that means the angles are much smaller. They're going through this wide part, which means the angles have to be much sharper. So they're defeating their purpose in two ways, and yet they still think it works. in spite of the fact that they got these 2 broken legs to start with. They already got 2 broken legs, and they're saying, I'm going to win the race. All right. So let's understand, gravity is made by the objects that have electrons and protons in them. It's the atomic weight, okay? Atomic weight that makes the gravity. And it's how dense it is the important thing. So if I have 1 electron and you come up very close to it, let's make you an X. Oh, I'm sorry, it's probably out of focus. If you're, let's just make it bigger, and then it won't be a problem. All right, so there's a gravitational object, and you're an X. So you can see if these were the units of gravity, the little atomic nuclear bits of gravity, you can understand that if you're close, it's going to be a strong force, and the more space I create between you and that body, the weaker and weaker. And it does it by this r squared thing, which means half the distance 4 times weaker. So just what it really means is, every radius is a 4 times the grade in the strength of the force. So you can understand that if this was a unit of heat, it would be very hot close, and it starts getting colder and colder and colder, substantially colder. Not a little bit colder, but a lot colder, very quickly. Again, the Earth is sitting very far from the sun, a million miles, whatever, long way, more than that. Anyway, and the gravity here from the sun is I think it is actually 0.00148 or something. It's incredibly weak. Anyway, and that's because of the speed issue. So we know that time in the gravity is how you collect the heat, right? So we can all agree on that if you want to collect heat, you have to be in it. You can't zoom through it real fast because then you won't collect any heat. So we're trying to collect heat. All right, and the simple argument is the further away you go isn't the way to collect heat. Even though you're going more distance, it's the degrade in the strength of the heat is twice the rate at which your distance increases. So as your distance is increasing, that is, I'm in it more, the temperature isn't just in a half, it's in quarters. So it's gotten twice as weak relative to you, 4 times weaker relative to the object. It's more than 4, obviously, at whatever your distance, 4 times the distance. So that would be relative to, say, an object. So I tried to simplify the point, which I don't even concede, but let's say a galaxy with its little spiral arms on edge, which is even sillier. Yeah, screw fell from nowhere. A little magic screw. Martians. I would already argue the galaxy is too weak. It can't even create light-bending gravity. Even though you're in it for a long time, the amount of heat coming off of it is so weak, it can't give you the number of BTUs. So let's say you need 10 BTUs. And you can't get them even at that point. And these people are saying they can get them way out here. And just by making this line longer, that's all I have to do. That's not going to do it. I mean, I see, how they're so dishonest, right? Because he quotes my video. Now, instead of taking the part that the point is, which is your distance increases by 9 times, that means the weakness of the force is now 81 times weaker. So instead of quoting that argument, that so what, you're in it 9 times longer, it's 81 times weaker. So if it was chlorine bleach or acid or anything else, if I gave you a choice, okay, spend 9 times longer in 81 times weaker acid, or spend 1 unit of time in the strongest acid, acid that is 81 times stronger than the other acid. Which one do you think is going to be better for you? Are you really stupid enough to say, yes, give me the 1-to-1 relationship? I don't want that 9 to 81 thing. That doesn't sound good for me. I mean, I said I would make it a heat argument. Now I'm making it a temperature argument. But I made it a dye argument, and hopefully they couldn't even understand that. If it was ink, and you're diluting it by 81%, and you have to get ink on the pen by sticking the pen into the ink is now 81% less dark. And you still have to collect a certain amount. You have to collect even more because now your angle is bigger. So now you need more, okay, ink than you collected when you were right next to the thing. And you know, he's arguing, he's defending this nonsense. All right. So let's see how this. So it's always a density argument. So as I'm trying to illustrate, so if you had a sun, okay, and it's made of hydrogen, which is really light. Like as I pointed out, I mean, you can do the math. I don't know what the exact numbers are. But if the sun was made of the same heavy elements that the Earth was made out of, and it was still the same size, its gravity would be something like 1,000,000 meters per second, or, you know, 10,000 meters per second. It'd be an incredibly strong gravity. Insanely strong. It would actually be 1,000,000 times, so it's probably going to be 8 million meters per second. Something like that. If it was made out of heavy elements. So it makes a huge difference that all these suns that are in this galaxy are, you know, suns. They're made of hydrogen. It's rice cakes. Okay, and then you're taking your rice cakes and separating them by distance. Alright? And they're saying this all adds up somehow. Well, no, it doesn't. It really subtracts. Every bit of empty space cuts the gravity that's coming off these objects by 1/4. Every single radius, 1/4 less, 1/4 less, 1/4 less. So it's diluting it, and when you put it in a circle, you can sort of understand that, oh, that's even more insanely diluted. When you try to turn it into a point object with a center of gravity, from a distance, that's it's more space than it is objects. So you're diluting. It's like you're making lighter and lighter hydrogen. So instead of making the sun heavier, you're making it lighter and lighter and lighter. The further away you go, it's getting lighter and lighter and lighter. It's losing its atomic weight at the inverse square rate. It's getting 4 times lighter. All right, so let's see. The real simple argument I thought anybody could get was what the inverse square law means is that as you go further away, the distance doesn't just get wider this way. So you're spreading something out. You have something that's 4-finger force. Well, if you spread the 4-finger force out, then you can sort of understand that when it gets close, I mean when you're further away, it's spread the goodies out. So if they were cookies, now the cookies here are only a mile apart, let's say. And when you go way far away, they're 10,000 miles apart. So if you're collecting cookies, it's going to be really hard to collect very many cookies because you have to wait 10,000 miles before you might hit another cookie. But the catch is that the inverse square law means their cookies are spreading this way also. So now you don't have much chance of getting cookies because the cookies are going in directions that aren't the plane you're on. So now you only have 1 out of the 10 cookies that are going to be available. They're not going to be on your plane anymore because they're spreading this way, and you're still one tiny little cookie collector. You didn't get any bigger. You're just going to spend a little more time on one single line. And there's a whole bunch of lines that the cookies are on that you'll never go anywhere near. And that's what the inverse square law means. All right, so again, yeah, so it's just back to this trying to understand it by something you know. So again, if it was acid that I make the sun out of, or I make it out of heat, you know, at least that's relevant. You can sort of understand that if you're really close, you know, you're going to get hit. You know, everything's shooting, the stuff is shooting off the thing, and there, you know, this is the, you know, how much heat is well, see, we'll just end up trying to point out it's spreading in both ways again. It's like, it's hard to draw the 4 dimensions so you can appreciate that it's going both ways. It's spreading both ways, up, down, and left, right. But you should be able to understand that if the thing is this size and you're this size, I mean, and even though you're only going to be in it for this short distance, at your speed, at your standard speed, that you're going to be exposed to a lot more here than you are way out here, where now look at your relative size is puny in terms of the rays coming out this way. You can see it with light bulbs, for Christ's sake. I mean, you get 100 feet away from a light bulb and it's almost, is it there? Is it on? It's not so obvious anymore. It's not anything close to obvious anymore. And so you're just this little tiny thing way out here. You don't get any bigger, all right? Yes, okay, you're in it longer, technically. I mean, if you just used an arc argument. But you got to understand too that doesn't work to your favor either, because these, this gravity is a lot weaker. This longer angle starts off even weaker. I mean, this is your strongest point, is the straight line, and it's really not coming at you at a straight line. So that's multiplied and just made worse. So, but anyway, let's just give it to you that you don't lose anything there. That's all you have. All you have is this longer distance, but your size is still puny. So you're only cutting a little tiny path through that longer distance. And again, as I pointed out, the force has spread these ways. So you're not getting any of the stuff that went that way. Alright, I don't think there's... I mean, I can keep trying to explain this, but what's the point? I mean, I think a kid can understand that if you put air in something, like you buy something at the store and it says 17 ounces, and if I pump a bunch of fake space in the bag, replacing the stuff that exists, well, let me think of another way. Try some other kind of material comparison. Like liquid. Well, let's say the liquid and the dye, in my opinion, that was a good enough analogy. You put 1 drop of dye in a gallon of water, and it turns the water a certain blue, let's say. You've got to know that if I'm going to put that same 1 drop in 10,000 gallons of water, that I'm not even going to see the blueness. And that if I have to collect it by just swirling something in it, you've got to understand that even if I'm swirling 9 times longer, if it's 81 times less blue, 9 times longer, 81 times less blue. That's the quote you need to play, Hofladay. Okay? 9 times longer, 81 times less blue. That's the inverse square law. So I'm arguing there's no lensing even possible on the edge of a galaxy, because like the Earth and the Sun, like the fact that the Sun is in incredibly low gravity, 0.001 meters per second. Anything on the periphery of a galaxy, right on the edge of the swirly bits. So you have the swirly bits, right, like here. The strongest gravity would be the Sun's right close, and you can see how far away they're going to be. I mean, the Earth would be in undetectable distance, and the Sun's gravity is already 0.001 just at an Earth's distance. This distance would be insanely far. So you're talking about something like let's just say 0.5 times 10 to the minus 32. Yeah, that's the number you're going to deal with. Oh, that was another irony. I mean, not irony. Another, oh, fuck you, Hofladay, you're a butthole. He said, oh, there's big G in the equation, the gravitational constant. The gravitational constant is a number like this. 0.5 times 10 to the minus like 21 or something. It's a preposterously tiny number. So you're gonna try to make your denominator bigger. See, I just turned your numerator. I can't remember now. I just multiplied. I turned it from, I just turned it into 81 from 1. Okay, so this number just got huge. That's being divided, and this is how much gravity influence. So gravity influence is going to be decided by this fraction. So I just turned it from 1 to 81. Okay, so now I'm dividing by 81, a monstrously huge number, which means this number is crashing down. Tiny, tiny. So the amount of dye you're going to be able to collect, that's what that number, it's crashing down because I just diluted your dye by 81. And the gravitational constant isn't helping you up here because it's a tiny, tiny number. So it's like, well, this ain't going to save you. This isn't going to make your denominator huge. This is going to give you nothing. It's going to add nothing to the strength of the crap on top. So you're not going to win. So I'm saying, look, the galaxy, like I said, something sitting here, putting a charge here, putting anything here, a tennis ball, doesn't matter what you put here. The gravitational influence is going to be a number this small. It's going to be a point 0.0000000, an insanely long 00 number. So you can't even bend light here. You can't collect enough dye even this close to a galaxy. You're still not going to collect enough dye. And the only hope you might have, as I keep pointing out, is, I guess I have such a poor drawing of it there that I might as well let me draw it a little better anyway. So this is what a galaxy sort of looks like in profile. So we'd say this is its gravitational fingerprint. They think anyway there's a lot of gravity in the center. I don't really think there is, to tell you the truth, but that's why, because it's something going, it's something leaving. It's not stuff being collected. So there's not a strong, the gravity is this. This is what causes galaxies to hold together. This and this are creating a binary system. The arms are gravitationally attracted to each other. They're keeping the thing from flying apart. It's just a bunch of binary systems. Binary system, binary system, binary system, cross, 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 cross. That's what the symmetry is doing for a galaxy. So it doesn't even need a dense center. And that's why the centers are often look empty. It's because they probably are empty. So I don't think physics, but let's just argue from your physics. So by your own physics, there's a big pile of black holes in here and there's a lot of gravity in the middle. And here you are lensing through this part over here. And you're lensing, not through this part, you're lensing way over here. Okay, all right? And so that's one big fat mistake. And again, just remember the angle, this angle and this angle. Oh, you sort of see this angle's a lot fucking bigger way out here. So you're killing yourself with your angle because now you need more bend. And you can't even do it here. It's so freaking weak. So if you were to have lensing, the plan would be if you went across this way, right? See, you could understand, look, the paper dipped in just the right spot there. You could sort of understand that this is going to be really strong gravity if black holes are here, because you're sort of close. I mean, you're a hell of a lot closer to the black hole than you are way over here. So, yeah, if you're going to lens something, if you're going to have a gravitational lens, it should be with galaxies on edge, okay? And this point is going to be the killer. This one's going to do this. This won't do shit for lensing. But once you get to that center, because there's all those black holes in there, this is where your light's going to bend and come to you, right to your little eyeball. All right, and the fact that none of you buttholes can understand these arguments, these simple fucking arguments, and you'll deny your own Einstein statements. I mean, Einstein said it. You're only going to find this lensing right around dense objects, big, dense objects. That's what's required. They have to be. They have to be solar masses in the sense that they have to be dense. Like, even though, like I said, hydrogen's a very undense substance. But at least the sun's not full of air. It's not full of empty space. If you filled the sun full of empty space, if for every hydrogen atom I added another, round ball of empty space, you could sort of understand that the sun would get bigger and the surface gravity would be much weaker. You can understand that. Yes, at a distance it's not going to matter much because you're just making the same amount of matter in the container size. So, but the bottom line is it's not going to give you more gravity. Going further and further away isn't going to help you any. And like I said, by the inverse square law, you're not expanding the hydrogen. You're not moving when this galaxy gets. When you're doing your lensing way out here, it's not because you took the matter in this galaxy and spread it out over this whole area. But it wouldn't help you anyway. I just... Anyway, it's just stunning that apparently every one of you, not a single one of you I've seen so far, not one single one of you obnoxiously arrogant fucks can understand the inverse square law. None of you. Not one of you can get it right and say, oh, Piro and Hathaway, you're so full of shit. And again, I just make the other argument. Why would they be arguing that it proves dark matter? Why would they argue that the lensing image proves the existence of dark matter? Why would they say something that stupid? Oh, that's right, because they have to make it prove dark matter, because the only way the math works is with dark matter. The only way you can make the gravity strong enough is to put fake matter right where the lensing is. Put a bunch of fake invisible men there so they can, you know, blow their heaters. Take hair dryers and blow them on the light to, you know, make it hotter so it bends. It's just, it's you know, well, anyway. I just can't believe I have to go over this again. You don't understand what I just you don't understand what I just said in this video. You don't understand this you know, galaxy this way versus the galaxy this way. You don't understand that. You don't understand that going around this hand requires smaller angles than going around this hand. You don't understand that. And you don't understand that if you're diluting something by 81 times, you're weakening the acid by 81 times. And you're going to be in it 9 times longer, that's the bargain you want. You don't understand that. That's weaker, not stronger. Okay. That's enough. I can't believe, like 5 videos on this? 4? I haven't gotten through Hotlities, but I only got a third of the way through it. He's just such a scum. Anyway, till next time. You know, he's always bringing up his stupid Asperger's. You know, there's no Asperger's. There's assholes. You're an asshole, Hathaway. And I mean, and saying psychiatrists say, yeah, that's like saying Bozo the Clown says the science of Asperger's. I'm sorry, no. It's the science of dark matter. Find any excuse to get out of jail. I'm an asshole. So instead of just saying you're an asshole, you got to say, oh no, I'm you know, specially enabled. Why? No. If specially enabled must mean asshole because you're behaving like an asshole. Every one of your personality traits is completely asshole-ish. You're just you're becoming the perfect image of an asshole.